You've probably heard that rainbows are formed by light interacting with raindrops. But did you know that all rainbows form as a result of that light bending 42 degrees inside the drop? In this video, I'm going to walk through a quick proof as to why, by looking at the physics that takes place inside of a raindrop. But first, I need to explain a few things about how light rays interact with the environment. When light hits a surface, part of that light reflects off symmetrically, like so. Mathematically, we say that the angle of incidence, theta 1, is equal to the angle of reflection, theta 2. But for less reflective surfaces, light is not entirely, reflected, and some travels beneath the surface and into the medium itself. This process is called refraction. Refraction obeys this equation, which is called Snell's law. The thetas represent the angle between the light rays and the line perpendicular to the surface, which physicists call the normal line. And the ends represent something called the index of refraction, which is a measure of how much a light ray bends when passing from a vacuum into a particular medium. For air, the end value is reasonably close to 1, which means that light hardly does any bending as a result of the density of air molecules. And for water, the material that makes up a raindrop, the end value is about 1.33. But because physicists like to be ideal, we'll call that quantity 4/3. And there we have an equation for how light refracts in a raindrop. So without further ado, let's take a closer look at what happens to light inside of a raindrop. A typical raindrop is roughly the shape of a perfect sphere. When light from the sun interacts with the raindrop, it initially refracts, then reflects off the back of the droplet, then refracts out again. I'll draw the normal lines and a few lines parallel to the line of internal reflection to make the incoming geometry a little bit easier. Let's call the incident angle phi and the refraction angle beta. Our goal is to use geometry to see the relationship between these two angles. Because angle of incidence is equal to angle of reflection with respect to its own normal line, we know that this angle is also beta. Now, something important to note about Snell's law is that it actually works regardless of which way the light is traveling. So if you don't mind, I'm going to surreptitiously reverse the direction of these light rays. Having done this, we can see that this bottom angle must also be phi, because it's the angle between incident light and light that experiences a bend upon entering water. That's just how we first defined phi. So by definition, this refraction angle also has to be beta. And by the same logic as we saw above, the angle of reflection with respect to its own normal is beta as well. Now let me draw your attention to this triangle for a second. Since the sum of the interior angles of a triangle is 180 degrees, this angle has to be 180 minus 2 times beta. And since two angles on a horizontal line should add to 180, that means that this blue angle also has to be 2 beta. From geometry then, we know that this top left angle must also be 2 beta. Thus, the angle between phi and 2 beta will have a magnitude of 2 beta minus phi. And all that having been done, we finally have an angle between the incident ray and its normal, so we can apply Snell's law like so. Of course, true understanding requires working through the algebra yourself, so if you feel up for it, go ahead and pause the video and give it a go yourself. I, however, will skip past it to save some time. Great! Now we have a general function for phi as a function of the angle beta. When we plot one against the other, we get this graph with a noticeable peak. As it turns out, this peak corresponds to the magical pair of angles which causes rainbows. Now, if you're like me, you might be thinking, why would it be this particular peak? This graph represents the variable magnitude of the angle between the horizon and the sun. It doesn't have anything to do with the intensity of the light, the size of the raindrop, or any type of physical quantity that one might expect to be tied to the scattering of light. But as it turns out, the reason for the rainbow's presence at this particular point is not due to the angle's maximum per se, but more so that this point happens to be the flattest. That means that a relatively large change in beta around this point corresponds to a relatively small change in phi. That means that many different values of beta can all get focused into about 2 times that angle. And the reason that angle is doubled is because the light gets refracted twice, once going in and once going out. So let's find out what that angle is. We can find the flattest point on the curve by setting the derivative equal to 0. Alright, let's do a little rearranging. Now, we could just plug this part into Wolfram Alpha and be done, but there's a somewhat interesting step in the algebra here that I think is worth examining. When we square both sides, we can take advantage of the fact that cosine squared is 1 minus sine squared. Then, after making that substitution, we have enough information to solve this equation purely analytically. In the final step, we receive a beta value of about 40 degrees, which, when plugged into the phi equation, yields a phi value of about 21 degrees. And doubling that angle finally lets us see the magical double angle of 42 degrees. But there's something I haven't explained yet. Why does the light split into different colors, rather than remain monochrome and white? The reason for this is that in reality, water doesn't have just one index of refraction. It actually varies based on the wavelength of the incident light. So the red component of sunlight, for example, gets refracted at a different angle than the violet component, which gives us the nice spread across the visible spectrum that we could come to expect from a rainbow. I've exaggerated it in this animation, but you get the idea. One last thing. If the light refracts twice inside the raindrop, rather than just once, we see a double rainbow, which will always form about 51 degrees, much like the first rainbow's 42 degrees. The mathematical derivation is largely identical to what I've just shown, but if you want to see it for yourself, I highly encourage you to pause and think about it as you go. And there you go.